Hello friends, welcome back to this series where we work through the book on quantum mechanics by Steven Weinberg. This is part 7 of chapter 4, which is all about symmetry transformations in quantum mechanics, in particular rotational symmetry. The topic today is a digression from this main theme. It has to do with how we describe the quantum states of multiple identical particles. By identical particles, we mean particles of the same species. These are features of a particle that are not changed by space-time transformations, such as rotations, translations, or Lorentz transformations. The quantum description of multiple identical particles leads to their classification into two broad categories. A particle can either be a boson or a fermion. While multiple bosons can occupy the same state, each single particle state can only be occupied by a single fermion of the same species. In this video, we shall explain what we mean by this and how this rule came about. First, let's start with a single particle state. To give a concrete example, assume that this is a state with a definite position and spin projection along the z-axis, denoted by sigma. This is a spin j particle. Now let's suppose we have two such particles, both of the same species, same spin. Both have definite positions and z components of spin. Thus these two particles are identical and can only be distinguished by their states. Each particle is assigned its own slot within the two-particle cat. Let's see what happens when we exchange their states. This state should be equal to the original state up to an overall phase. That's because the two-particle state contains the same collections of states assigned to identical particles, and so should be physically indistinguishable from the original state. Furthermore, this overall phase alpha can depend only on the species of the particle, and should not depend on x and sigma, or any other eigenvalues that could be changed by space-time transformations, like rotations, translations, or Lorentz transformations. Here's why. Suppose alpha does in fact depend on the positions and sigmas. Let's apply some space-time transformation u to both sides of the equation. As we have said earlier, the positions and sigmas will change under this transformation. By what we have assumed above, the argument of alpha should also be x prime and sigma prime. This implies that alpha should be independent of x and sigma. Thus we have shown that the overall phase alpha can only depend on the species of the particles. To further constrain alpha, let's perform another exchange. This should give us another factor of alpha. On the other hand, making two exchanges should also give us back the original state. This implies that the square of alpha is equal to 1, which has two possible solutions, alpha equals to +1 or -1. The +1 solution are the bosons, which have states that are symmetric under the exchange of particles of the same species, while the -1 solution are the fermions, which are anti-symmetric. Let's gather our results into this red box, B for bosons and F for fermions. To simplify our notation, we label the state of each particle by xi. Specifically for the case of the fermion, we have This means no two fermions of the same species can share the same state. This is the famous Pauli's exclusion principle, which was first devised by Wolfgang Pauli to explain the states of electrons in atoms. We can generalize this result to n identical particles. For some arbitrary permutation p of the states of the particles, we gain a sign delta p according to the rules above. Note that the exchange of two particles is also known as a transposition, as in the red box. For the boson, delta p is just equal to 1 for any permutation, while for fermions, delta p is equal to the sign of the permutation. This is calculated by assigning each transposition of the permutation with a minus sign. So an even permutation, which contains an even number of exchanges, has a plus sign, while an odd permutation a negative sign. Let's see some examples. N equals 2 and 3. Let's see how we can construct these symmetric or antisymmetric states from the tensor products of single particle states. For two particles, this is straightforward. We shall ignore the normalizations of these multi-particle states for now, but note that all the single particle states themselves are normalized, and that they form an orthonormal basis. By the same logic, the symmetric and antisymmetric states for n identical particles can also be constructed from single particle states. This is done by summing over all the permutations of the tensor products of xi1 to xn, together with the appropriate permutation signs. Let's check that this construction does indeed give the correct signs under permutations. Let's reorder the state above by an arbitrary permutation P'. P colored blue is summed over, and so is like a dummy variable. We can therefore replace all the P under the sum by the composition of P with the inverse of P'. Note that the sign of the composition of the two permutations is just equal to the product of the sign of each permutation. The sign of the inverse of P' can be taken out of the sum. The sign of the inverse of P' is just equal to the sign of P', since both contain the same number of transpositions. This term in the red box is just the original state. Hence our construction above does indeed give the correct permutation sign. An important point to note is that a particle can either be a boson or a fermion, but not both. Take the example of two identical particles. If it is possible for this system to be in a symmetric state, that is, the particles are bosons, while at other times they could be found in an antisymmetric state, which implies that they are also fermions, then it is surely possible for the two particles to be in a superposition of these two states. But the resulting state would then not have a definite sign. This violates the property that any state describing a system of identical particles should have, according to our earlier argument. Therefore, all states available to a set of identical particles must have the same sign. In this way, any superposition would preserve this sign. Thus our point is proven. What about a composite particle that is composed of n particles? Nb of them are bosons and Nf fermions. What happens when we exchange two such composite particles? We would pick up signs from the constituent bosons as well as the fermions. The overall sign from such an exchange depends solely on the number of fermions within the composite particle. Therefore, if there are no fermions, the composite particle of any number of bosons is still a boson. On the other hand, if all the particles are fermions, then the composition of an odd number of fermions remains a fermion, while an even number of them makes a boson. These rules of particle compositions are consistent with the addition of angular momenta of the particles. An important result from relativistic quantum field theory, known as the spin statistics theorem, states that particles with spins that are of integer values are bosons, while those with half-integer spins are fermions. If we write spin as an integer n divided by 2, then n is even for a boson and odd for a fermion. Recall how two angular momenta J1 and J2 are added. The resulting angular momentum J could take values between J1 plus J2 and the absolute value of their difference at integer intervals. Suppose both J1 and J2 are of integer values. Then the resulting total angular momentum J must also be of integer values. We can see this from a simple calculation. Both the upper and lower bounds of J must be integers. So two bosons is equivalent to another boson. This is consistent with the first rule above. It is easy to see that adding more integer value angular momenta to J will continue to give a range of integer value angular momenta. Whereas if both J1 and J2 are half integers, then J should be an integer. Two fermions make a boson. This is consistent with the second set of rules above. What about the composition of a half-integer and an integer spin? We can see J2 as the result of summing two half-integer spins. Here we see that adding a third half-integer spin will give a range of half-integer valued spins. We can see a pattern emerging here. An even number of half-integer spins is equal to a set of integer spins, while an odd number of them gives half-integer spins. This is consistent with the composition rule for fermions above. These examples hint at a connection between the spin of a particle and its statistics, which is proven in relativistic quantum field theory. Let's go back to the earlier construction of the state of n identical particles out of single particle states. These states are particularly useful if the Hamiltonian of the system can be approximated by the following form, which acts on each individual particle separately. Terms like this one, which couples together two particles, are missing. A and B are two non-trivial operators. Each particle just experiences the action of some single particle effective Hamiltonian. This effective Hamiltonian describes the interaction of one given particle with all the other particles. Each particle experiences the potential due to the rest of the particles, while it is assumed that the latter feels no back reaction from this one particle. This is known as the Hartree approximation. Let's find the eigenstates of this Hamiltonian. This is straightforward. All we have to do is to find the eigenstates for the single particle Hamiltonian. These states are denoted by psi A. The index A labels the different eigenstates. Ea is the energy of a single particle. We need to modify our notation for the multi-particle case by including the particle label I, since different particles could be in different states. The bosonic or fermionic solutions to the total Hamiltonian is just a symmetrized or anti-symmetrized tensor product of the single particle energy states. Consequently, the energy of this state is simply the sum of the energies of all the particles. This is so because the permutations performed to effect dissymmetrize or anti-symmetrization does not affect the value of the total energy. Inevitably, we would like to make measurements on the eigenstate capital Psi. Suppose this measurement is made in a basis where each particle is in some state Xi, which, as a basis for identical particles, would also need to be symmetrized or anti-symmetrized. To be more concrete, let's assume Xi to be the eigenstates of position and spin projection. What is the wave function of capital Psi in this basis? Let's calculate this directly from the two expressions above. Look at this product of two permutation signs. This is just a sign of the composition of permutations. Now look at this product of inner products between the states Psi and Xi. This product should remain unchanged if we apply a further permutation to all the particle indices. Let this additional permutation be blue P inverse. This undoes the original blue P permutation. This yellow permutation associated with the inner sum is just like a dummy index, so we can modify it with an additional blue permutation. First of all, this sign will be transformed into, which is just equal to the sign of the yellow permutation. And the rest of the terms become. Notice that the inverse blue permutation is neutralized. All these inner products are the single particle energy eigenfunctions in the state space of Xi. Thus we have the energy wave function of n identical particles. For the case of bosons, the sign is always equal to 1, and we just have the sum over all the permutations of the variable Xi with respect to the single particle energy states. The symmetry of the particle indices of this wave function is apparent. For n fermions, the sign delta is conveniently represented by the epsilon symbol. Note that we are using the Einstein's convention here, where repeated indices are summed over. Let's recall the definition of the epsilon symbol. For even permutations of n indices, it is equal to 1, while for odd permutations, minus 1. This expression is the well-known Slater determinant. We can see that it's a determinant from the Leibniz formula. The matrix in question is the single particle wave function. One application of this expression is in describing the state of multiple electrons in an atom. Let's explore this wave function further. How would operators in the n-particle state space act on this wave function? Let's go through a simple example that is particularly relevant. Let's look at an operator that acts on each particle separately, like our Hamiltonian from before. A1 is a single particle operator. Let's see how A acts on the wave function psi in the state space of xi. For the single particle state, this is straightforward. Just insert the identity operator in the xi basis. The integral xi actually contains both a sum and an integral. This term is the single particle wave function, while this term is the matrix representation of operator A in xi space. Thus we have the action of A on the single particle wave function. For the case of n identical particles, we just need to know how A acts on each term within the sum in the definition of psi. Our calculation becomes easier if we rewrite the wave function in this way. A moment of reflection will convince you that these two products are equal. Each of the terms in A acts on each single particle wave function in the product according to the rule in the blue box. Like so. We can express this result in terms of the definition of the wave function for n identical particles. This is how an operator of the form like A acts on the wave function of n identical particles. We can apply this directly to the Hamiltonian from before. Very often, we would have the expression of H in xi space. For example, as in the usual Schrödinger's equation in one dimension. But more about this in future videos. Next, we move on to one of the greatest achievements of quantum mechanics in the early decades of the 20th century. This is the theoretical explanation for the periodic table of chemical elements. The key idea is the Pauli's exclusion principle. We will also need the results from lecture 14 about the spectrum of the hydrogen atom. More accurately, we have an atom like hydrogen, except that it is overly ionized, with a nucleus with Z units of positive charge, paired with a single electron. We have derived the energy of this electron as given in the yellow box. These energies depend only on the principal quantum number n. The states that correspond to these energies are also the eigenstates of the orbital angular momentum of the electron, as well as its intrinsic spin. Now we shall fill up this ionized atom with the rest of the electrons to make the neutral atoms of the periodic table, with Z as the variable that distinguishes between the different elements. The Pauli exclusion principle becomes an important constraint in how we perform this task, since no two electrons can occupy the same state. Let's see what are these states. For a given value of n, the orbital angular momentum L are all the integers between 0 and n-1. Again, we have derived this in lecture 14. As usual, the magnetic quantum number m lies between L and -L. Being spin half, the electron can only have two possible spin projections along a given axis. To keep things simple, we shall retain only the relevant variables in the energy En. Recall that n is a positive integer. Let's make a list of all the orbital states. We are using the spectroscopic notation. The first number is n, while the second letter is L, where we are using SPDF, etc. for 0, 1, 2, 3. Each row is limited by the constraint on L, and its states have the same energies. States differing by the quantum number m is not displayed explicitly. So are the spin states, but let's make a note of their numbers. Now we fill these states with Z electrons, starting from the lowest energies. But note that in doing so, we are assuming that the electrons in an atom do not interact with each other and only interact with the nucleus. This is a very unrealistic assumption. Instead, the actual arrangement for the multi-electron elements looks like this. Note that states are arranged in layers with increasing energies downwards, forming energy shells. The scheme on the right is obtained from the naive model on the left by using an empirical rule known as the Mendelong's rule, where we fill the states in increasing values of the number n plus L. And when two states have the same value, we choose the one with lower n, like so. To really justify the more accurate model on the right, detailed calculations need to be done, taking into consideration how the electrons interact among themselves. We shall not do this in this video. Rather, we shall give a hand-waving argument. Look at these states in the red boxes. They are out of order compared with the arrangement on the left, since they have lower values of n. They make up for this by having higher L's. This is in accordance with the Mendelong's rule. This rule also implies that among states with fixed n, the higher the value of L, the higher the energy. But our energy formula for hydrogen-like atoms only depends on n and is independent of L. Recall that the potential associated with these energies is just the Coulomb potential, where we have ignored the interaction among the electrons. Here we introduce a hand-waving argument that allows the potential to depend on L. More accurately, the electron in an atom experiences a different potential depending on its L value. Let's consider the innermost electron. This electron experiences the potential due to the full charge of the nucleus, which is completely unshielded by the outer electrons. This is the consequence of Maxwell's theory of electrodynamics, assuming that the rest of the electrons are distributed in a spherically symmetric way. And as we have said earlier, this potential corresponds to the following energies. If we fix the number n for the state of this electron, the energy of the electron could still increase if its angular momentum L increases. Here's why. Recall that way back in lecture 10, the radial part of the energy eigenfunction goes like r to the power of L as r goes to 0. Thus, the larger the value of L, the less likely the electron is to be found at the center of the atom, and so on average would be further away from the nucleus. Perhaps like so. Our electron moves past W number of electrons as its angular momentum increases. These electrons act as a shield on the positive charge of the nucleus, which modifies the potential felt by the electron. The atomic number Z is effectively changed to Z minus W. Thus, as the angular momentum of our electron increases, the effective Z of the potential acting on it decreases. And this in turn leads to the increase in energy, even if N is fixed. This is consistent with the Mendelong's rule. And this concludes our crude attempt to verify this empirical rule. What we have done is take into consideration the interactions between the electrons by including the shielding effect on each electron by all the other electrons. Now let's count the number of available states in each energy shell, which we shall fill with electrons. The total number of states in each angular momentum orbital consists of 2L plus 1 times 2 states. The lowest energy consists of just the s orbital, which contains 2 states and could hold one electron spinning up and another spinning down. The second shell contains an s orbital and a p orbital. So we have 2 states from s and 6 states from p, according to our formula above. We proceed in this way, summing the states in all the orbitals on each shell. Each of these states can hold only one electron. For Z equals 1, we have only one electron in the lowest shell. This is hydrogen. If Z equals 2, we need 2 electrons. These fully filled the first shell. This is the helium atom. For higher values of Z, we need more electrons, which would have to go on the next shell. The second shell can hold 8 more electrons. This results in the elements lithium-3 to neon-10. Z runs from 3 to 10. As before, adding more electrons to balance the increasing values of Z, we would fill up more and more shells. Adding 8 more electrons will fill up the third shell, with argon-18 as the element with 3 completely filled shells. 18 more electrons will give us krypton-36 with 4 full shells, and so on and so forth. Elements with all full shells are a group of inert gases known as the noble gases. These elements are the least reactive because the electrons in their outermost shells are more strongly bound to the atom due to the shells being completely filled. Let's see why this is so. If we just look at a particular electron on the outermost shell, this electron will fill a potential with some effective Z. Assuming that N is the number of electrons on the outermost shell, the effective Z is the bare Z value of the nucleus, minus the total number of electrons in all the inner shells. This represents the full shielding effect of the inner electrons. And finally, minus half times the rest of the outermost electrons. This half is to take into consideration the partial shielding effect of these electrons on that one electron, because electrons on the same shell can only shield each other partially. And so we have this result. The effective Z reaches its maximum value when the outermost shell is completely filled. N full is the number of electrons it takes to do so. We can see that the potential experienced by an electron in the outermost shell is the deepest when the shell is full. This is the case for the noble gases, which is why they are the least reactive. Their outermost electrons are the most tightly bound to the nucleus, and therefore could not engage in electron sharing, which is required for 2 elements to bind together to form compounds. This formula allows us to define a variable that is a good measure of the reactivity of an element. This is the valence of an atom, which is defined to be n if n is less than half of n full. In this case, we have a positive valence. For n greater than half of n full, the valence is defined to be n minus n full. In this case, we have a negative valence. An atom of positive valence has a tendency to give up its outermost electrons to an atom of negative valence to form a chemical bond. If the valence of the two types of atoms complement each other like so, the two atoms will share electrons to complete each other's shells to form a stable bond. Note that a full shell corresponds to a valence of 0. For an atom of valence 1, the sole electron on the outermost shell is held only by a shallow potential, according to the formula above. As a result, this electron is easily lost, which makes the atom very reactive. Atoms with valence 1 are known as the alkali metals. Complement to the alkali metals is a group of elements with valence minus 1. The outermost shell of these elements are one electron short of a complete shell. These elements are known as the halogens. Examples are fluorine, chlorine, and bromine. These atoms have a tendency to pick up an electron from other atoms. Even though each atom is neutral, due to the imperfect shielding of the positive charges of the nucleus, the atom could still have a Coulomb attraction for other electrons. We can see this from our earlier calculations. As we have said, the positive charges of the nucleus is balanced by the total negative charges of the electrons in the atom. To estimate the potential experienced by a typical electron on the outermost shell when extra electrons are added, we would have to modify this last term. Like so, delta n is the extra number of electrons shared from another atom. This modifies our result for effective Z. Notice that this Z effective is still positive as long as delta n is less than n plus 1. This means the potential would still be attractive, even though the total charges are no longer neutral due to delta n. For our example, where the valence is equal to minus 1, the total number of electrons in the outermost shell is one short of a full shell. This gives the following effective Z. An atom of valence minus 1 likes to take in one electron. This is positive, since a full shell contains at least 2 electrons. Furthermore, this is the maximum value Z effective could take, so the attraction is strongest. In this way, our atom is able to attract outside electrons and forms chemical bonds with other atoms. Less reactive than the alkali metals are the alkali earths with valence equal to plus 2. They are less reactive due to the fact that such atoms have one less electron on the inner shells, and so the nucleus is shielded less effectively. Thus the atoms held on to their outer electrons a little more strongly than for the case of alkali metals. Examples are beryllium, magnesium, and calcium. Our logic so far has been that electrons with the highest energies in an atom are also the outermost electrons, which are most responsible for interacting with other atoms. Therefore, the states of these outermost electrons will determine the chemical properties of the atom. However, there are exceptions. This is when the outermost electrons are not those of highest energies. Why this is so has to do with the details of the wave functions. The orbitals that correspond to these cases are the following. Both are f orbitals, which contains 14 states. Although these are the occupied states of the highest energies in their respective atoms, the s orbital states below them in energy are actually the outermost orbitals, and so are responsible for the chemical properties of the atoms. These are the Lanthanides, which runs from lanthanum-57 to actinium-70, a series of 14 elements, and the Actinides, that runs from actinium-89 to nobelium-102, also 14 elements. The 14 elements within each series have very similar chemical properties, because their outermost electrons are on the same s orbitals. Let's summarize our results on the periodic table. The atomic number Z of the elements increases from left to right. Each row is known as a period, each column a group. The elements in each group have very similar chemical properties as they have the same valence. These rows correspond to the energy shells from earlier, with the angular momentum orbitals color-coded. Each orbital contains a number of states given by the formula 2l plus 1 times 2. The groups that form the columns at both ends are the noble gases and the alkali metals. The next columns inwards are the halogens and the alkali earths. The lanthanides and the actinides are the elements with their highest energy electrons in the f orbitals. The general rule is that the chemical properties of atoms are determined by their outermost electrons, and the outermost electrons usually have the highest energies, except for the lanthanides and the actinides. Let's look into energy shell models in general and see how they work with Pauli's exclusion principle. Starting with the atomic shells. Let's take the 4 lowest levels as example. We have all these shells, each composed of degenerate states. These are states with different angular momenta, and by the simple model of the hydrogen atom, they all have the same energies. But this is an exception rather than a rule. We expect there to be some small variation in energies within each shell for more realistic models of the atom. The most significant energy difference comes from these energy gaps between the shells. For the case where all the lower states are filled with electrons, like in the example illustrated here, we have the structure of the noble gases. Since for the electrons at the top level to interact and form chemical bonds with other atoms, they must be able to make transitions to other states. But the only available states are across a significant energy gap on the next shell. However, if the topmost electron is the only electron within the shell, then there are plenty of states available for transitions with very low energy costs. This results in reactive elements like the alkali metals. Complement to this case is the halogens, which is one electron short of a complete shell. This vacancy thus allows room for transitions to occur. Notice that such reasoning will fail if electrons are bosons instead of fermions, and many electrons could occupy a single state. The Pauli's exclusion principle is thus critical. Recall that way back in Lecture 5, we have used the same reasoning for electrons moving in the periodic lattice of a solid. This lattice is represented by a periodic potential with period L. In general, each electron in such a potential will move within continuous energy bands, which are separated by energy gaps. This is the result of the Bloch's theorem. Each band is parametrized by a continuous wave vector, Q, which values are constrained within a finite domain known as the Brillouin zone. For more details, refer back to Lecture 5. The link is in the description. Here, we are only interested in the energy structure. One feature is strikingly similar to the previous example of atomic shells. This is the fact that the energy difference within each band is small, compared with the band gaps. In fact, they vary continuously. And therefore electrons within each band makes transitions to neighboring states within the same band much more easily compared with crossing the band gaps. So we could again make use of the Pauli's principle to describe the characteristics of the solid. If a band is completely filled with electrons, they are thus locked in by a band gap, making them less responsive to external perturbations. In this case, we have an insulator. This is an analogy to the noble gases for the case of atoms. While if we have a band that is only partially filled, the electrons would thus have plenty of states to move in, making them more responsive to external perturbations. We then have a conductor. This is an analogy with the more reactive atoms from our previous example. Due to the success of the atomic shell models in the early days of quantum mechanics, the next logical step would be to apply similar ideas to describe the nucleus. Specifically, what are the states of the nucleons within the nucleus? Once again, since these are spin-half particles, we are dealing with fermions, which must obey the Pauli's exclusion principle, just like the electrons. But in this case, the attractive forces between the nucleons are no longer due to the electromagnetic interactions between the positive charges, and is instead the result of the strong interaction between the nucleons. This force acts with similar strength for both the protons and the neutrons, from what is known from nucleon scattering experiments. On top of this, we have the electromagnetic repulsions between the protons. This is a much weaker force, but of a longer range, and is balanced by the short-range nuclear force. The resulting net potential is what we will be modeling for the nucleus. The problem we shall tackle has to do with what is known as the magic numbers. These are the numbers of nucleons that form very stable nuclei. Their stability is seen in this way. For example, take a nucleus with 8 nucleons. If we add an extra nucleon to this nucleus, it is observed that the binding energy for this additional nucleon will decrease sharply when compared with the neighboring cases of 7 or 9 nucleons. The binding energy of a nucleon is the amount of energy required to knock it out of the nucleus. Let's write down the Hamiltonian for a nucleon in a nucleus. We shall assume a simple nuclear potential. R is the radius of the nucleus. This potential assumes that the nucleus is spherically symmetric and corresponds to a radial force. This force ought to be zero at the center of the nucleus due to spherical symmetry, which implies that the first derivative of V should be zero at the origin. This explains the quadratic form of V. In fact, this is a good approximation for the region around the local minimum of a general potential and should give us good results for light nuclei that lie near the bottom of the potential. V0 is the depth of the potential and is an undetermined parameter of the model. We have also assumed that the potential cuts off sharply at the surface of the nucleus due to the short range of the nuclear force. Let's substitute in V. We shall replace the parameter V0 by introducing a new parameter omega. This is inspired by the harmonic oscillator. Omega is the vibrational frequency of the nucleus. This implies, which gives us omega in terms of the rest of the parameters. The motivation for this change of parameters is to be able to use our results on the 3D harmonic oscillator from lecture 18. The eigenvalues of this Hamiltonian is given by n is the energy quantum number that takes integer values. These energy states are also angular momentum states, since the 3D harmonic oscillator is rotationally invariant. Since the depth of the nuclear potential, V0, is just an ordinary number, these energies are directly modified by minus V0. We are mainly interested in the low-lying states of smaller n, as this is the region where the harmonic oscillator is a good approximation for the nuclear potential. V0 should therefore be greater than the preceding terms. This implies negative energies, as should be expected for bound states. Now we can define the binding energy of a nucleon on level n by just the negative of En. This is quite intuitive, as the higher the energy level of a nucleon, the less it has to climb to escape the potential, and therefore the lower its binding energy. Let's examine the energy shells for the nucleons within the nucleus, according to our model. These shells are equally spaced, with separations of h bar omega. As before, each shell contains the angular momentum states, which is approximated to be of equal energies. Of course, we also need to include the spin states of the nucleons, as we did for the electrons within an atom. Both of these are conveniently spin-half particles. Another result from lecture 18 is this relation between the quantum number n and angular momentum L. This serves as a constraint on L for each level n. D is the degree of the Laguerre polynomials, which is part of the radar wave function of the 3D harmonic oscillator. Similar to the case of electrons for each L, the number of states is 2L plus 1 times 2. This comes from two spin states. With these two relations, we could calculate the number of states available on each energy shell. This calculation is also done in lecture 18. Thus, the degeneracy for a given n is the expression in the red box from lecture 18 times 2 to include the spin states. Using the constraint in the blue box, L takes the following values with separations of 2 for a given n. Let's fill in the orbitals for each level. Starting with n equals 0. This allows only L equals 0, which is the s orbital and corresponds to two states. For n equals 1, for n equals 2, this time we have two possible values for L, s and d. For the s orbital, we have this number, and d orbital, which gives a total of 12 states. Now for n equals 3. These are the available states which we shall now fill with nucleons. A nucleus with only the first shell filled contains two nucleons. One with two full shells carries a total of 8 nucleons. 3 complete shells contain 20 nucleons. 4 shells, 40 nucleons, and so on and so forth. Now let's examine the binding energies of these nuclei, which are composed of completely filled shells. As before, let's take the number 8 as an example. This nucleus is filled up to the second level. If we add another nucleon to this, the only available states are on the next shell. This nucleon will move up the potential well by h bar omega, thus reducing its binding energy by the same amount. Compare this with nuclei with the neighboring nucleon number 7 and 9. The binding energy of the added nucleon in these cases changes by only a small amount, since this nucleon remains on the same shell as the topmost nucleons of the original nucleus. Thus those nuclei with these numbers are very stable, since it is not easy for the nuclear potential to capture more nucleons, as these have sharply reduced binding energies. These numbers that came from our model are very close to the magic numbers from empirical data. In fact, the first three numbers are in perfect agreement. But we have a problem when we reach the fourth number. We ought to get 28 instead of 40. This is the point when we have to refine our model. Let's add an extra interaction to our Hamiltonian. What we hope is to split the fourth shell into two shells, with the lower shell as the new fourth level. We would like to introduce a modification to our nuclear potential that will preserve the rotational symmetry of our system. An obvious choice would be to import directly from what we use for atomic systems. Recall that we have introduced the spin-orbital coupling back in lecture 21 to explain the fine structure of the atomic spectra. This is a modification of the Coulomb interaction of the hydrogen atom by taking into consideration the magnetic interaction between the spin of an electron with its orbital angular momentum. For nuclear systems, such a coupling is not due to the electrodynamics of the nucleons, but rather it is an effective model that results from the more fundamental strong interaction. Therefore, it is similar in magnitude for both the proton, which has an electric charge, and the neutron, which is electrically neutral. In this case, the operator S is the nucleon spin. As we shall see, to better fit the empirical data, the coupling function F should be negative in magnitude. Here we shall just retain the sign of the coupling. We can rewrite this in terms of the total angular momentum J. We need to find the eigenstates of this new Hamiltonian, now with the spin-orbital coupling. The eigenstates we have assumed for the original Hamiltonian are no longer suitable. What we need is something that is also simultaneously the eigenstate of J square, L square, and S square. This is possible because all these operators commute with each other due to rotational symmetry. Recall that J is the generator of total rotation, rotating both orbital and spin vectors. Thus what we need is this set of eigenstates. Delta V acting on these gives the following. Let's substitute S equals half. To evaluate this expression, we need the possible values of J for a given L and spin half. This is easily obtained from the rules of angular momenta addition from lecture 21. For the case of L equals 0, J is just equal to half. There is no energy shift for this case. We shall just focus on the case for L greater than 0. For the first value of J, we have and for the second value, Substitute this result back into delta V. So we see that the states with J equals L minus half and J equals L plus half are shifted differently, leading to an energy splitting proportional to 2L plus 1. This splitting is precisely what we need. The lower states, which correspond to J equals L plus half, is the new fourth shell. Their harmonic oscillator quantum number is still n equals 3. Let's verify that we have the correct result. We shall assume that only the splitting of the f orbital matters. Since the magnitude of the splitting increases with L, and the f orbital has the highest angular momentum among these lower states, L equals 3 gives J equals 7 over 2. This corresponds to 8 angular momentum states. Thus, if we now fill all these 4 shells completely with nucleons, we get the number 28, which is exactly what we need. So the harmonic oscillator potential, modified by the spin orbital coupling, gives a compelling description of the magic numbers of nuclear stability. For inspiration, here's a page from the course notes on nuclear physics from 1949 by Enrico Fermi. The digitized version of these notes are available for download on the website of the University of Chicago. The link is in the description. We have reached the last topic of this video. This is the application of our results on the quantum states of identical particles to the case where we have a macroscopic number of particles that is in thermal equilibrium with its environment. To do this, we simply have to plug in the appropriate quantum states into the formalism of statistical mechanics. If you are unfamiliar with this topic, just check out the first video of our series on statistical mechanics. The link is in the description. If not, let's continue. The key object for describing the properties of a system under thermal equilibrium is the partition function. Here, we have shown the more general grand partition function. In this situation, the system not only can exchange energy with its environment, but also particles. Capital I here labels the states of our multi-particle system. Beta is 1 over the Boltzmann constant times the temperature of the system, and mu is its chemical potential. If the total particle number is a conserved quantity, then the particles will flow from a system with higher chemical potential to a system with lower potential. For derivation of this result, refer again to our video on statistical mechanics. From this partition function, we can calculate the probability of the system to be in state I. This probability is simply proportional to the Boltzmann weight of the state, for the case where the interactions between the particles are weak, and that all the particles are identical and have access to the same set of single particle states. The total energy of the system is simply equal to the occupation number Ni of each state times its energy, then summing over all possible single particle states. Little I labels each single particle state. The total number of particles is just the sum of all occupation numbers. Note that capital I, which labels the multi-particle states, is now replaced by a set of occupation numbers. Now we can rewrite the partition function of the system in terms of the occupation numbers by using the relations below. This multiple sum factors out nicely in the product of contributions from each single particle state. We can view each term in the product as a partition function for each single particle state, Zi, and because the Boltzmann weights are similarly factorized. The probability P⁻I also factorized into the product of probabilities. Each probability is the probability for a single particle state to have a given occupation number. Therefore, all we have to do is to calculate Zi. For the case where all the identical particles are bosons, there are no restriction on the occupation numbers. Zi is an infinite geometric series, which has the standard result. For the case of fermions, due to the Pauli exclusion principle, no more than one particle can occupy each state. Ni can only be 0 or 1, so there are only two terms in the sum. Note that we can summarize these results in a single expression. The upper signs correspond to bosons and the lower signs fermions. Another expression which we shall often use is the average occupation number for a state. This is defined in a straightforward manner by our probabilities for occupation numbers. We can express this in terms of the derivative of log Zi with respect to the chemical potential. Now plug in our explicit expression for Zi. Thus we have the average occupation number for state I for both bosons and fermions. Let's apply this formula to two examples, first for the case of bosons. We shall derive Planck's distribution for the energies of photons in a box under thermal equilibrium. The box has sides of length L and volume V and is kept at temperature T. We wish to calculate the energy carried by the photons within this frequency interval per unit volume, or similarly, we can do so for the angular frequency omega. The two frequencies are related by 2 pi. Omega is related to the wave number k by the speed of light c. Even better, let's calculate the energy carried in the corresponding interval of k. Let's look at the number of states in the volume in the momentum space of k. There is one momentum state in a momentum space volume of 2 pi over L cubed. If we assume a periodic boundary condition, this is a convenient assumption as long as the box is large enough and the bulk properties of the system is insensitive to the exact boundary conditions. The number of states in this interval is therefore given by. This is the volume of a spherical shell of thickness dk divided by the k volume associated with a single state, multiplied by two spin states. The spatial volume V cancels out. Let's express this in terms of omega using the first equation above. The energy carried in this interval is the number of states multiplied by the average number of particles in these states times the energy of each photon. This is the occupation number of a photon state with frequency omega. Using the expression in the yellow box, we have The chemical potential mu is 0 in this case, since the number of photons is not a conserved quantity in this radiative process. They are continually emitted and absorbed by the walls of the box. Let's express this in terms of the frequency nu using the second relation above. Recall that h bar is defined as h over 2 pi. Thus we have derived the Planck's distribution for the blackbody radiation using the particle statistics for bosons. For a second example, let's look at fermions. We could consider a gas of identical Fermi particles. This Fermi gas can describe the free electrons moving around on the lattice in a solid. This distribution of particles takes a particularly simple form as the temperature goes to 0. For states with energies greater than mu, no particles can occupy those states. All states with energies less than mu are occupied by one particle. This is because the exponential in the denominator goes to infinity for one case and 0 for the other. The surface that separates these two regions is known as a Fermi surface. Thus, if we now add another particle to the system, it must then sit on top of this Fermi surface and so has energy mu. This is why one of the ways we can understand the chemical potential is that it is the energy added to the system when one particle is added. There is a situation where it doesn't matter if the particles are bosons or fermions. That's when the exponential term in the denominator is very much larger than the second term, which carries the sign that differentiates between bosons and fermions. Under such conditions, the occupation number is approximately an exponential function. This is the Maxwell-Boltzmann Statistics. The condition above implies that the average occupation number for any state is very small. This is why it doesn't matter if we have bosons or fermions, the Pauli's exclusion principle is simply not tested. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.